So, welcome everybody to our next lecture on deep learning. Today we want to talk about optimization.
We have a search technique which is just local search, gradient descent.
Now let's have a look a bit on the gradient descent methods in a little bit more detail. So we've seen that the gradient is essentially optimizing the empirical risk. And here in this figure you see that we do one step each towards this local minimum, and we have this predefined learning rate eta. So the gradient is of course computed with respect to every sample, and this is then guaranteed to converge to a local minimum.
The stuff that works best is really simple.
Now, of course, this means that for every iteration, we have to use all m samples, and this is called batch gradient descent. So you have to look in every iteration for every update at all m samples. These may be really large, in particular if you look at big data, computer vision problems, and so on.
With, say, image recognition or something like that?
So this is, of course, a preferred option for convex optimization problems, because we have a guarantee here that we find the global minimum, and then every update is guaranteed to decrease the error. Of course, for non-convex problems, we have a problem anyway, and we may have really big memory limitations. So this is why people like to prefer other things like the stochastic online gradient descent, the SGD, and here they use just one sample and then immediately update. So this is no longer necessarily decreasing the empirical risk in every iteration, and it may also be very inefficient because of the latency transfer to the graphical processing unit. But however, if you use just one sample, you can do many things in parallel. So it's highly parallelizable. A compromise between the two is that you can use a mini-batch stochastic gradient descent, and here you use B, and B may be a number much smaller than the entire training data set of random samples, that you essentially choose them randomly from the entire training data set, and then you evaluate the gradient on this subset B, and this is then called a mini-batch. Now this mini-batch can be evaluated really quickly, and you may also think about parallelization approaches and so on, because you can do several mini-batches in parallel and then just do the weighted sum and update. So small batches then are useful because they offer a kind of regularization effect. This then typically results in smaller eta. So if you use a mini-batch stochastic gradient descent, typically smaller values of eta are sufficient. And it also regains efficiency, and typically this is the standard case in deep learning. So a lot of people work with mini-batch stochastic gradient descent. Well, the question is, how can this even work? And our optimization problems is non-convex, so there's an exponential number of local minima. And there's an interesting paper from 2015 and 2014. They show that the networks that we are typically working with, they are high-dimensional functions. There are many local minima, but the interesting thing is that those local minima are close to the global minimum. And actually many of those are equivalent. What is probably more of a problem are saddle points. And another thing might also be that the local minima might even be better than the global minimum, because the global minimum is attained on your training set. But in the end, you want to apply your network to a test data set that may be different. And actually, a global minimum on your training data set may be related to an overfit. Maybe this is even worse for the generalization of the trained network.
And that was my 1987 diploma thesis, which was all about that.
There is one more possible answer, and this is a paper from 2016. He's suggesting over-provisioning. So there are essentially many different ways how a network can approximate the desired relationship, and you essentially just need to find one. You don't need to find all of them. A single one is sufficient. So this has also been verified experimentally by experiments with random labels, and here the idea is that you essentially randomize the labels. You don't use the original ones, but you just randomly assign any classes. And if you then show that the way you're experimenting still solves the problem, then you are creating an overfit.
And there is very little theory behind the best solutions that we have at the moment.
Now let's have a look at the choice of either, and what we've already seen, that if we have a small learning rate, then we may stop even before we reach convergence. If you have a too large learning rate, then we might be jumping back and forth and not even finding the local minimum, but only with the appropriate learning rate you will be able to find your minimum. And actually, when you're far away from the minimum, you want to be able to make big steps, and the closer you get to the minimum, the smaller your steps want to do. So in practice, you work with decay of the learning rate, so you adapt your either gradually. So you start with, let's say, 0.01, and then you divide by 10 in every x epochs. So this helps you to bring you really to a decaying learning rate, and you don't miss the local minimum that you're actually looking for. It's a typical practical choice.
So that's stuff that's really stood the test of time.
Now you may ask, can't we get rid of this magic either? So what is typically done, quite a few people suggest doing line search. So line search, of course, needs you to estimate the optimal EDA in every step. So you need multiple evaluations necessary in order to find the correct EDA in every step. And the direction that we have is extremely noisy anyway. Still, people have presented methods, but this is not the state of the art right now. Then people have suggested second order methods, but if you look into second order methods, you need to compute the Hessian matrix, and this is typically very expensive to calculate. So far we have not seen that. Too often there's these ABFGS methods, but they typically don't perform very well if you're operating outside of the batch setting. So if you work with mini batches, they are not that great anyway. And there's a report on that by Google that you can find in reference number 7. What else can we do? Well, of course we could accelerate directions with persistent gradients. So the idea here would be that you somehow keep track of the average that is indicated here with nu v, and this is essentially a weighted sum over the last couple gradient steps, and then you have the current gradient direction, so you somehow average the previous steps with the new one. The new one is indicated in red here, and then this gives you an updated direction. And this is typically called then momentum. So we introduce this momentum term where you add with mu weighted some momentum that is indicated with v, k minus 1, and this momentum term is essentially computed in an iterative fashion where you iteratively update over the past gradient directions. So you can essentially say by iteratively computing this weighted mean, you keep a history of the previous gradient directions and you gradually update them with the new gradient direction. And then you pick the momentum term in order to perform the update, and you don't pick just the gradient direction. So typical choices for mu are 0.9, 0.95, 0.99, or you even adapt them from small to large. So you want them to pay more emphasis on the previous gradient directions. This overcomes like poor Hessians and variance and stochastic gradient descent. It leads to damped oscillations, and it accelerates typically the optimization procedures. Still, we need the learning rate decay. So this doesn't solve the automatic adjustment of either. We can also pick a different way of momentum. That's the Nesterov accelerated gradient, NAG, Nesterov momentum, and this performs a look ahead. So here we also have this momentum term, but instead of evaluating the gradient at the position we're currently at, we add the momentum term before computing the gradient. So we're essentially trying to approximate the next set of parameters. So we use the look ahead here, and then we perform the gradient update You can rewrite this to use the conventional gradient, and the idea here is to put the Nesterov acceleration directly into the gradient update, because this term will then be used in the next gradient update step. So this would be an equivalent formulation. Let's visualize this a bit. So here you can see momentum and the Nesterov momentum, and of course they both use the kind of momentum term, but they use a different direction for calculating the gradient direction because they plug it into the update call. So that's the main difference. Here you see an example of these momentum terms, and this is a situation in which you have a strong disagreement in the variance in both directions. So we have a very high variance to left and right, and rather little variance to top-bottom variable, and we are trying to find the global minimum, and this then leads typically to alternating gradient directions very, very strongly. Even if you introduce the momentum terms, you still get this high oscillating behavior. And if you use the Nesterov accelerated gradient, you can see that we compute this look ahead, and this allows us to follow the blue line. So we are directly moving towards the desired minimum, and we are no longer oscillating. So this is an advantage of NAG. Now, what if our features have different needs? So suppose some features are activated very infrequently, while others are updated very often. Then we would need individual learning rates for every parameter in the network. So we need large learning rates for infrequent parameters and small learning rates for frequent parameters in order to accommodate the changes appropriately. And this can be done with the so-called AMSGrad. And the AMSGrad method is using first the gradient to compute some GK, and then it's computing the product of the gradient. And it keeps track in R the product of the gradient for each dimension. So this essentially allows us to compute a kind of variance for each dimension. And now we use RK, and RK is of course used element-wise as a vector here in combination with eta to weigh the update of the gradient. So now we construct updated weights, and the variance of the weights in every dimension is incorporated by multiplying with the square root of the respective element. So here we note this down as a square root of an entire vector, but all the other things here are scalar, which means that this also results in a vector again, and this vector is then multiplied pointwise with the actual gradient. So this implies a local scaling. Very nice, efficient method, and it allows individual learning rates for all of the different dimensions, for all of the different weights. Then one problem could be that the learning rate decreases too aggressively. This is one problem that then leads to improved versions, and the improved version here is RMS-prop. RMS-prop is now using this again, but they introduced this rho, and now rho is being used to essentially introduce a delay, yes, that you don't have the very high increases, and here you can set this in order to dampen the update of the variance of the learning rate. So Hinton suggests rho 0.9 and eta 0.001. And this then leads to the aggressive decrease being fixed, but we still have to set the learning rate. If you don't set the learning rate appropriately, you run into a problem. Now Ada Delta tries to improve on this further, so they use essentially RMS-prop for computing this RK. So we already seen this. This is the variances that are computed in a dampened way. And then in addition, they introduce this delta x. And now delta x is somehow a weighted combination of some term h and the r that we had seen previously, multiplied to the gradient direction. So this is an additional dampening factor that replaces the eta in the original formulation, because delta x is then used to update the weights. Then this factor h is computed again as a dampened sliding average over the delta x inner products. So this is other delta. Here you don't have to set individual learning rates anymore. Still you have to choose the parameter rho, and here for rho it's suggested to go to 0.95. One of the most popular algorithms that are being used is Adam, and Adam is essentially also using this gradient direction in G. Then you have essentially a momentum term. So here Vk is the momentum term that is introduced for the gradient. Then you have this R term that is again trying to steer the learning rate for each dimension individually. And then it introduces an additional bias correction where the Vk is scaled by 1 minus mu k, and R is also scaled by 1 over 1 minus rho k. This then leads to the update, the final update term that involves the learning rate eta, our momentum term, and the respective scaling. And this is then called adaptive moment estimation, ADAM. Now suggested values are mu 0.9, rho 0.999, eta 0.001. Very robust method, very commonly used. You can combine it with the Nesterov accelerated gradient and you get an ADAM. But still you can improve on this. And this is then AMSGrad. So AMSGrad is another improvement on ADAM, because ADAM was empirically observed to fail to converge to optimal or good solutions. And in reference 5 you can even see that ADAM and similar methods do not guarantee to converge for convex problems, because there's an error in the original convergence proof. And therefore we suggest to use AMSGrad that fixes ADAM to ensure non-increasing step size. So here you can fix it by adding a maximum over the momentum update term. So if you do this, you result with AMSGrad, and this is now shown to be even more robust. So the effect has been shown in larger experiments. So one lesson that we learn here is that you should keep your eyes open. Even things that go through scientific peer review may have problems that are later identified.
And while I was reading that, I was already typing the response, and they had to publish it because I was right.
And another thing that we learn here is that these gradient descent procedures, as long as you approximately follow the correct gradient direction, you still get quite decent results. So very interesting. Yeah, and of course, such gradient methods are really hard to debug. So be sure that you debug your gradients. This really happens, as you can see in this example, that even in large software frameworks, bugs or errors occur, and for a long time people don't notice them. They just notice strange behavior, but the problem persists.
And then if you're a development engineer, or if you have the development build like I do, then you can see all the debug information. But those would just be like total gibberish to most people.
Right. Okay, so let's summarize this a bit. Stochastic gradient descent plus Nesterov momentum plus learning rate decay is a typical choice in many experiments. It converges most reliably. It's used in many state-of-the-art papers, but it has the problem that this learning rate decay has to be adjusted. Adam has individual learning rates. The learning rates are very well behaved, but of course the loss curves are much harder to interpret because you don't have this typical behavior as you would see them with fixed learning rates. What we didn't discuss here, we only hinted at that, is distributed gradient descent. Of course you can also do this in a parallelized manner and then compute different update steps in different nodes of a distributed network or on different graphic boards and then average over them. And this has also to be shown to be very robust and very fast. Some practical recommendations: start using mini-batch stochastic gradient descent with momentum. Keep to the default momentum. give Adam a try when you have a feeling for your data. Yeah? When you see that you have already set things quite nicely, then Adam can help you with getting better or more stable convergence. You can also switch to AMSGrad, which is an improvement over Adam. And of course, start adjusting the learning rate first, and then keep your eyes open whether everything still works. And then in later steps, go ahead to AMSGrad and things like that, because then you can get even more stable training. Okay, so this brings us towards a short outlook on the next couple of videos. And what we are coming up is, of course, the actual deep learning part. We haven't discussed deep learning at all so far. So one problem that we still need to talk about is how can we deal with spatial correlation in features. We hear so much about convolution in neural networks. Is this a good idea? Why is it? How is it implemented? And then, of course, one thing that we should think about is how to use such invariances and incorporate it into network architectures. Some comprehensive questions. What are our standard loss functions for classification and regression? So, of course, L2 for regression and cross-entropy loss for classification. You should be able to derive those. This is really something that you should know, because the statistics and those relations are really important. The statistical assumption, probabilistic theory, and how to derive those to get to our loss functions. Very important, subdifferentials. What's a subdifferential? How can we optimize in situations where our activation functions have a kink? What's the hinge loss? So how can we incorporate constraints? In particular, how can we tell it to people that tell us, oh, your stuff is not good because SVM is superior? Well, you can always show that it's up to a multiplicative constant, the same as using hinge loss. And then, what is Nesterov momentum? Describe Adam. Very typical things you should be able to explain. If somebody in the near future is going to ask you questions about the things that you have been learning here. Some further readings that we also put into the description of this video. Very nice introductions for losses and some insights about loss functions. And of course, we have plenty of references. Again, this may be too quick to go through all of those references. So you can stop the video, pause it, and you can also find them in the description of this video. I hope you enjoyed this video as well, and looking forward to see you in the next video. Thank you very much.